what can you say about the relationship between price of a car and the revolution per mile? So this one is cars they are selling. And so if a customer comes and you have to interpret this graph to the person in order to help the person buy a car. There was. There are, I think it's revolution or something per mile. Yes.
Engine speed.
Yes. So what you said is correct, but will you say this to a customer? In other words, what is the customer interested in? If I'm going to buy a car, is it the revolutions per mile that I'm interested in? Is the price, yeah. So your interpretation should go with what? The price. Yeah. Yes. So that's one aspect, that if a car that is cheaper will have what? More revolutions per mile. Something like that. Okay. So let's look at another one. There is also a data set called cars. So cars is just the speed and distance of a car. But this one is they are just two. If they are just two, look on the, so you see the speed and distance. So they check the braking distance of a car depending on the speed at which the car is traveling. Okay, so we can, it looks like this. So how would you, if you are the Road Safety Commission, and we have collected data on cars and the speed at which they were traveling, the distance they need in order to brake such that you don't hit the object in front of you. And this is a graph you have obtained. How would you interpret this to a trotro driver at circle? You have the distance and speed.
At high speed, it takes a longer distance for the car to stop.
So
if you are driving so that high speed, you need a longer braking distance.
you need a longer. So what are you going to tell the driver? Road safety. So you are now with the Road Safety Commission, and you have to advise drivers. You have shown them this, and then you say this. So how do you? So break it down such that any. What you are saying is correct, but come to the layman's point of view. Yes. You are from the Road Safety Commission. So your duty is to what? Prevent accidents, educate drivers to prevent accidents. And you have this graph. How are you going to communicate? Yes.
The car moves very fast.
Yes.
It takes a longer distance for you to brake. So you are moving, so they should reduce your speed so that if you have lower speed, it takes a shorter distance to stop, so that you don't crash.
So that you don't crash. Okay. So that's what we want to hear.
So that you don't crash.
Yes, you need to interpret it so that they really understand. And you can go and point. So I can point here and tell them that if you are, let's say, around 8 miles per hour. You just need maybe about 5 meters or something to brake. But if you are traveling at 25 miles per hour, you may need as high as what, 120 meters to brake. Other than that, you hit the next object in front of you. Yeah. So that's how you brake this down to a driver. Is everybody okay with this? Okay. So let's look at, in terms of correlation, what will be the correlation between the two? Positive correlation, okay. So let's see how we can do this in R. So correlation. So when there is positive correlation, we know what it is, right? And so forth, okay. Now, so we have core. It's for correlation. So X, we just go here, and X will then be what? Cars. And then we select speed, and then Y will be what? Cars. We select dist. Okay. Then we run it. We get 0.8. So you see that you have what? Positive correlation. Now, how do you interpret this? 0.8. What can we say? Did you also get 0.8? Good, okay. What can you say about this? If you have to interpret this to the drivers as well, what are you going to say? Today we are only treating driving. We have to talk to the drivers. So let's see, how are you going to interpret this? Yes. Oh, you just, if you're able to interpret the other one, then you should be in a position to interpret the other one too. Yes. Who will try? If there is positive correlation, what does it mean? Yes. Good, yes. As one increases, you expect the other to increase. Similarly, as the other decreases, you expect the other to also decrease. So how are you interpreting it now? You said the higher, but speak in terms of how the driver will understand.
So the lower the speed as we did drive, the lower the accidents, that's okay. Because it takes them a shorter distance to brake.
Okay, come again. The lower the speed, the shorter.
Yes, if you see lower accident cases.
Okay, yeah. So that's fair enough. Okay. So you see, we can all do the same thing, but the way we interpret it will be, it's all talking about the same thing, but we can interpret it from different angles. Okay. But usually, use examples that people will really understand to communicate statistics. Otherwise, it would look abstract to everyone. So here we say that there is a positive correlation between what? The distance of the car and what? The speed at which it is traveling. The braking distance of the car and the speed at which it is traveling. What this means is that if you are traveling at a higher speed, then you require a longer distance to brake. If that within that distance there is an object there, then you are likely to hit it. Yeah, so it means that if you also travel at a lower speed, you need a shorter distance to brake. In that case, there would be no accident, because you can easily get some distance to brake before you hit the next object. So that's it. Now, in correlation, we have the Pearson, Kendall, and Spearman correlation. The Pearson is the most widely used, and then the Spearman and Kendall's are for when we have ranks. Is that okay? So by default, it takes the first one. So what we have gotten is the first one, the Pearson. Okay. So I want us to check how we can get the Kendalls as well. If we can get we want to get a Kendall, we can delete the Pearson, then the Kendall becomes first. Okay. So let's delete that. If we delete that and we run it, we're going to get what's the problem? No, I think I did not select all of them at a go. So call something is wrong. Oh, I left. Okay, so let's just leave just the Kendall, right? And of course, this one you can take out the C as well if you want. So that is like that, yeah, 0.68. So you see that Pearson was 0.8. This one is what? 0.668. Remember, if we want to use the Kendall, we have to convert the actual speed and the distance into ranks. In other words, the speed, which one is the highest, will be rank 1. The lowest speed will be ranked the last number. Then we go to the distance. The longest distance will be 1. The shortest one will be the last number. Then when we finish, we have to count. For Kendall, you count the number of concordant sets and then discordant. So the number of is half. The number of concordance minus number of discordant divided by half into the n times or the n minus 1 or 2, n minus 2. And that will give us the Kendall's rank correlation. Okay. Then we also have the Spearman, which we know as 1 minus 6 sigma di squared divided by n into n squared minus 1. Okay, so we can also get the Spearman. So just copy this, paste, and then change this to Spearman. Okay. Now you see this one too is what? 0.83. So they all give you different results, but usually the sign will be the same. It's just the magnitude that differs. So the signs will be the same. Okay, so this shows that the relationship between the speed of the car and the distance is positive. It means once you increase your distance, your speed, you require more distance to brake. Okay. We can look at other examples, like let's also check the insurance data. I think we did talk about data like the auto claims. So auto claims, we have amount paid and age. So maybe I want to check whether there is a relationship between age of the policyholder and the amount paid. So we can check to see what. So the first thing you do is just a plot, right? That always helps to check age. And then y will be equal to age. Oh, no, claims. Paid. Okay, so let me see. Not not anything we should worry ourselves about. Okay, so it's not there's okay, there's a data on cabbages. So cabbages, you want to study the relationship between the vitamin C content and the head weight. So this is agricultural experiment. So if you go to a shop to buy cabbage, which one should you buy? Is it the one with the big head or the one with the smaller head? Which one has more vitamin C? So that's what we want to study. In that case, the vitamin C will be our dependent variable, and the head weight will be what? The independent variable. Is everybody okay with this? Yeah. So usually in a question, nobody, or when you are at the workplace and somebody brings you, they will tell you, I want to study this. I know that it has a relationship with this. Nobody will tell you that this is dependent, this one. It's the way the question is framed. So here, I mean, the weight of cabbage is easily obtained at the shop. You just put it on a weighing machine, you'll get it. If you want to see the vitamin C content, you have to send it to a lab. By the time they finish, you won't even be able to eat the cabbage. Or maybe they have to take a sample of it and then you send it away. So in this exercise, we want to see whether we can get a relationship between what? The vitamin C content and what? The head weight of cabbages. So we will let X be cabbages, and then we select what? Head weight, right? Okay. And then, of course, Y will be what? Cabbages. So you see, each time I start typing and then I select. I don't type in full. Once you do that, you are likely not to get what? Any, errors at all. But if you type this, a high chance you get this. No, cabbages is not in insurance data, it's in math. The auto claims is in insurance, yeah. The insurance data. You wanted to ask?
Would it matter which one you select for X and which one for Y?
So in correlation, it doesn't matter.
Okay.
But because we will transition to regression, then you need to know which one is your Y, which one is your X. In the regression that you are doing, you must always get some Y, which will depend on certain variables. So here, we are only studying this, so this is how it looks like. So we can go in and let the SLR be equal to head weight, and then this one is in kg. If you look at so let's say in an exam, when I ask you to do something like this, I expect that you go and study the health files of the data and know what to label it with. So the head weight is in kilograms, if I'm not mistaken. We can check. Cabbages. So if you come down here, yes, head weight in what? kg. So you label it such that anybody that sees your work will know what it's about. You don't need to even explain what it is. And the VC is what? Ascorbic acid content. So we can just make it vitamin C or vitamin. It's with C is fine. That one is a bit easier too. So this is it. Now how are you going to interpret this to a farmer or a will be, let's say you are at the shop, or you go to one of these fairs and you are selling cabbages. How are you going to explain this to a will-be buyer of your cabbage?
The lesser the weight of the lesser the weight of the cabbage.
Yes.
The more vitamin C.
The vitamin C content.
Okay. So that's one.
And
Who
the
else?
more it is, the less vitamin.
The more.
The bigger the size,
Yeah.
the less vitamin, like my brother.
So
It's bigger, nothing is
we say use example. This example you when you finish and he corners you at the back, don't call us. Okay, so yeah, but so yes, you said that if you pick one with a higher, has a larger weight, the vitamin C content will be very low. So, and this is a real data set from experiment. So it means that when we go to the market to buy cabbages, we should rather go for the smaller ones. Yeah. So we get it. So let's see the correlation. So now, once you interpret it this way, before you even compute the correlation, you know what you expect. Sometimes you can make mistakes, or you can even compute something that is different from what you. So the correlation, the data you supply, will even be different. But because you know the graph, if you get positive now, you should be worried that cannot be the case. We expect to get what? A negative correlation. So let's see how we can get this. So core, we can just select this. But once we have done X and Y, we come to the top, we copy, and then we paste it inside. So we don't waste much time. So it's negative 6.5, 0.65. So here, there is almost a strong negative correlation between what? The ascorbic content of the cabbage and its weight. Okay, so the more, the heavier the head, the less vitamin C you find in the cabbage. That's it. Okay. So that's correlation. Now, when you correlation to, we have tests concerning the correlation coefficient. Okay, so we want to see. So the fact that you collected this data and it is giving you negative 0.65, that is descriptive statistics, right? You saw that in your inferential class, you cannot make any conclusive conclusions when you have descriptive statistics. Okay, we need to check, and usually for correlation, you want to check whether there is actually a negative correlation between them, or there is actually correlation between them. If you say correlation, it can be positive, it can be negative, and so forth. So in hypothesis testing, you may be interested in testing H0 rho is equal to 0, and then the H1, there can be three ways we can test H1 rho not equal to 0. Is that okay? Of course, we can also test whether the correlation is equal to a particular value. Yeah, but usually this is one. Or we can also test rho greater than what? 0. Or we can check rho what? Less than 0. Is everybody okay with it? Okay, so these are the tests we can do concerning the correlation coefficient rho. Now to do this, we use what we call core.test. Core.test. So let's see, it's the same as, so what it does, what? It tests for association or what correlation between what? Paired samples. You can only find correlation if you have what? Paired samples. It must have its X and what? Y component. Other than that, you cannot find any what? Correlation between them. All right. Now, so this is how it looks like. Core, we can put formula in it now as well, depending on how the data is structured. But the way our data is in the what data the cabbages, we can just, let me look at the way it is, because you can use any of them. So let's just highlight only this and run. So this is how it looks like. So if you look at the top, yeah, we have just what? VC, head and VC. Okay. So, and then you have C39 and what have you. Okay. So now let's see. We can just copy X and Y, just like that. Just copy all this. Yeah, and then you come and paste down. Copy your core, you paste it down, you put .test there, right? And then we can move on to check other things. Method, if it is Pearson, you leave it like that. Is that okay? But if you want Kendall or Spearman, you must state it. Okay. Then there's also exact. That's not quite interesting. We can leave it. But the other interesting argument is conf level. That is the confidence level. Remember, your confidence level can be 90, it can be 95. Usually we use 95. So you see, by default, this is what? 95. So, but if we say 90%, you can also what? Change it to what? 0.9. All right. So here, what are we checking? We are only checking, then I forgot to add alternative. So copy alternative and come and put it in. I'll explain what it is. So you see the first one is two-sided. Rho not equal to 0 is a two-sided. If I were to ask you to test whether there exists a negative correlation between the VC and the head weight, then you can choose your alternative to be what? Less. Okay, or if we want positive, then you choose it to be what? Greater, and so forth. So here we are only interested in what? Whether there is this significant correlation. So we just leave the two-sided like that. Okay. So that's it with this, and then we can run it. So run it and let's see how we interpret the results. Unexpected symbol. I think I did not. Yeah, after this, there's no comma. Yeah. So there should be a comma here. If you like, you can delete all this as well and leave only what? Two-sided. And then I rerun it again, I get my results. Okay. So the correlation will be the same as what we did earlier, which is negative, so and so, but we need to interpret this one. So please finish and then we can all do that together. Yes. I remove the method too. Okay, but it will just take the default, which is piercing. Yeah. If we want to use the spearman, we will come back and put method is equal to what? Spearman. Okay. Can we move on? Have you gotten the results? Okay, good. So let's look at how we will interpret the results. Now look at the first one. Pearson's, so it will always show you which of the three correlations it is computing. Cool. And then the data is what? Cabbage head weight and cabbage odd weight C. Then this is the T. So this test is a T, right? It's a T test. So we can read this value and go and read its, if we know the degrees of freedom is there, 58. So we can read a T at what? 58. Degrees of freedom 58 at 0.0025. We can use how to read it and what? Interpret the results. Or we can also use the p-value. What is the argument for the criteria for using the p-value? If the p-value is what? Less or equal to, in this case, 0.05, what will you do? You reject the null hypothesis. So you look at what is over there. The p-value is what? 9.75 times 10 to the power negative 0. So it's quite small. So what do? We reject the null hypothesis. What is the null hypothesis? What does that mean? No, rho is equal to 0 means no correlation. So if we reject that, what do we mean? There is a significant correlation between what? The VC content and what? The head weight. So that's our conclusion. Now another way to look at this is through the confidence interval. So we use the p-value to make a conclusion. We can also use the confidence interval. Now for the confidence interval, we look at our H0. H0 is a stethoscope. Rho is 0. So we'll check whether our interval that we have computed encloses 0. So look at it. The lower limit is what? Negative 0.78. The upper limit is negative 0.48. Does this include 0? No. So what do? We reject the null hypothesis. Is everybody okay with this? So that's how you use it. We can also use a T and read from table. That is a long way to do, but we can try that as well. So remember that when we did distributions, when we have Q, it's quantile, right? Yeah, so we can use a QT. The P will be 0.95. No, in this case, 0.975 or 0.025. Because it's two-sided, you have to divide them by 2, 0.975. Then the degrees of freedom will be what? 58. So you do this, it gives you 2, right? If I had used a 0.025, I'm going to get negative 2, 0.0 something. So you go to your estimate and check the t. The t is negative 6.6. So if you look at negative 6.6, it's going to be way at the rejection region. If you remember what you did, it will be like this. So this one, we are rejecting for small and what? Large value. So this will be negative 2.00. This will be 2.00. So if it is here, these are the rejection regions, both sides. So negative 6 will be somewhere here. So where is it? It's in the rejection region. So what do? You reject. So that's yes.
Please, do you mind going through it using
The confidence interval.
no, the T value?
The t value. So you calculate the t. From the sample, the t is negative 6.68. What we don't know is, in the exam they give you t tables to read. Yes, that's what we read from the R. That's a QT, and we got 2, which means, remember the t distribution, this should be 0. So on the left side, you get the other side of it. Yeah. So you check, negative 6, where will it be? Somewhere here, which is the rejection region. So you reject the hypothesis. So whether you use a t, you use the confidence interval, or you use the p-value, you arrive at what? The same conclusion. Okay. So that's it with this. And then, after this, we can then move on to regression itself. So now regression. Any question on the correlation before? So you should be able to compute correlation. You should be able to interpret it and also test whether there's a relationship between them. Yes.
About the critical value of resistance.
Yeah.
So, I mean, like, I also know that if the critical value is greater than the t statistic,
Yes.
then you fail to reject.
No, it depends on.
Yeah, so
What?
I was going to say that in interpreting this, can we say that because the absolute value of the t statistic is greater than
Yes.
the critical value,
Yes.
then you reject?
You reject, yeah.
Okay.
Yeah, because here, when it is at the other side, 6, if we find the absolute value, it will be greater than the 2. Yeah, so you reject. Yeah. Okay. Is everybody okay? Can we move to the regression part? So what we have done now is to be able to study relationship. We are able to say, as this increase, this one will increase. As this decrease, this one will increase. Something like that. Okay. What it doesn't tell us is what is our interest. Okay, so here, I'm only interested in vitamin C content. I want to get vitamin C, so I want to eat cabbage and get it. But the cabbages, when I go to the shop, have sizes. So I want to be able to know which one I should buy. And there's a scientific study that gave us this data. And we've been able to determine the relationship. The other side of it is now to fit a model so that if I go to the shop and I weigh the cabbage, in most shops you can weigh it and know the price you will pay. So once they give it to me and I have this, my formula on whether I can just calculate it on my phone and say, well, if let's say the weight is 10 kg, then I expect that the vitamin C content should be, let's say, this one. So that's the other part of it. So if you come here, what we want to do is to be able to now get a model so that if we go to the shop and let's say the weight is 2.5, we expect that we should be able to estimate the vitamin C content. as at now, if it is 2.5, I can over here to give me something like this. If I go up here to give me, so you won't know. But if we have a line, it will just give us 1 point. So that's the next thing we want to do. Okay. To do that, in R we use what we call LM. Yeah. So which is linear model. So LM. So LM fits what? Linear model. This is our last week. Oh,
No. 2 more.
oh no.
And this week for 2 more. 2 more.
We are doing 6 weeks.
Yeah.
We have, oh no, we haven't finished the 6.
No. But next week we meet twice.
Next week,
2 more.
Yes.
2 more weeks.
2 more weeks.
Yes.
But we can finish again.
So this is the 4th week.
Yes.
No.
And the 4th week has ended.
What is
From-
true?
The 4th week has ended.
I've been teaching how you say it's going. Okay, I thought it was 6 weeks. Okay. So, which means, let me see. Because we have to plan for our exams too. Let's see. So you mean we are going to end where? 15th.
15.
Revision week. 1 week. So exam will take us to
So this one and then this. Then we start the exams when?
Like 29.
2 weeks now.
No. That will be
Yes, like 29.
Prof, they say August.
Yes, 29.
Yes.
59.
The last
Saturday,
Saturday
Sunday.
and Sunday.
Okay.
Friday. We start Friday as usual. I hope we are 1 to 3.
So we have to start 29.
Friday.
We have to finish early so you can concentrate on your projects because the next graduation will be somewhere December or January.
Wow.
So if we have to graduate you within the next 2 months, we have to get everything done. Other than that, you come back next year. Middle of next year for yes, or the last one. Okay, so let's see. This one fits. So 29 is I have to start getting the timetable ready. Okay, so it goes like this. Formula. So let's copy. We are only copying up to the data. The rest you can read around it, but essentially we just need these two. So like this. And we are going to name it Fit LM1. So that's the name. You can decide to give it any name you want. So the formula is usually y on x. So what is your y? Our y is what? Cabbages with C, isn't it? Okay. So cabbages with C. Then we need the tilde sign. That is on the top left of your this. But we can't, if I do it, it won't fit over there. So I come down. So the tilde sign, then I'll copy cabbages again. And then head weight. Is that okay? Okay. So head weight. Then the data, I don't even need that. So because the data is there, I can just call cabbages. Then all I need is just what? With C, and it recognizes it that way. Please, are you okay? Once I give LM the data, I don't need to call the data again. I can just use the heads. But you have to make sure that the column heads are the same as it is written. Okay, so like this, and it fits well, nothing. And then after that, I do summary. So we have summary, LM, and so forth. You can use that one or just the normal summary. Like this. So summary of the model you fitted. And then you run it. And then we'll go through the results. So get the results and then we go through it. So this one is our own name. You can give it any name you want. The formula will always be y on x. So what's your y on x and then the data that you want. You've done multiple regression. So when we finish, we can also add on other variables like the species and so forth. And then it explains even more of the variations we see in the vitamin C content. Okay, can we move on? Not yet. Okay. Don't type, or you can copy from the other side. You go to the office. Okay, can we move on to look at the results? Okay, so now let's see the results. When we do summary, we get something like this. The call is the formula we put in. So our formula is called LM vitamin C and the data is cabbages. Good. Then the residuals. So what are the residuals? Well, if you look at the line, the residuals will be what the line is giving us and what? The actual values. So that's the residual. Now, if the model is good, we expect the median of the residual to be 0. And the max and the minimum must be of the same value but what? Different signs. Right? Because the idea is, okay, before then, let's just do AB line. And then it will AB line this. Make sure your plot is this. So AB line, then color. Let's give it a color of red. Okay, and then maybe we make the line width a bit bigger. So 2. So there it is. So AB line actually draws what? The fitted line. If we give it the model we have fitted, AB line will draw the fitted line through it. So if we look at this one, the distance between this value and what the model is telling us is the residual. Is that okay? Now, if the line is good, then because it must pass through the central part of it, those up will give us positive, those below will give us what? Negative. So you expect that they will what? Cancel out, so that the average, on average, it becomes what? 0. If I add them, it should become 0. Okay, so if the results differ so much from 0, it's an indication that the line is not all. It's not the best. And as you see, this one, all of them are not on the line. If all of them are on the line, we'll get the residuals to be 0. Yeah, so that's what. Leave it. Okay, so that's it with the residuals. We can also look at it. We want it to be somehow normally distributed, right? So we can, when we are doing diagnosis tests, we can plot a histogram of it. We can also even check whether it is normally distributed by using the Shapiro test on the results and so forth. Okay, so let's see. Maybe like what else do we? So okay, we were trying to understand this. Okay, so that's this for the residuals. If you look at the residual, we'll plot it later on. It's not that, look at the minimum and the maximum, they are a bit close. We also expect the third quarter and the first quarter to be a bit close, which is the case. 5.0, there is a difference, but not so much, right? And this one is a bit close to 0, but not exactly equal to 0. Okay. Then we come to the coefficient. This is a simple linear regression. So your model is of this form. So we have some y, and y has this plus an epsilon, right? And then now we've been able to find some y like that. X. Okay, so this is the straight line we have now. Okay, so that beta naught is the intercept. And then beta 1 is what? The one with the head weight. Is that okay? Good. So the next one is what? The estimate is 77.54. The other one is negative. So if the correlation is negative, we expect the beta 1 to also be negative. So now the question is, how do we interpret these values? So you have y cap. The model is y cap is equal to 77.57 minus 7.57x. How do you interpret this? Yes. How do we interpret this in relation to the problem we are dealing with? Let's start with the 77, the beta naught. Yes. Yes. No one. Yes.
Y hat is equal to 77.57 when x is set to be 0.
Okay. When s is said to be 0, what does it mean? So when you are interpreting this, it must be because you are going to talk to farmers or a potential person who is buying at the shop. If you say x is equal to 0, the person will not know what you are talking about. So whatever we are interpreting should be in relation to the data we are talking about, or the data at hand. Yes. What is x in this case?
It's a head weight.
Head weight. So when S is equal to 0, what does it mean? If the head weight is equal to 0? No cabbage. Okay, so when the weight of the cabbage is 0, it doesn't make sense. Is that okay? If you have cabbage, you say the weight is 0. Then maybe if it is in space, it can give you 0. But it doesn't. So sometimes, naturally, x is equal to 0 does not exist. Is that okay? So in this case, it doesn't. It makes it a bit impractical to say that the cabbage has 0 weight, but it has vitamin C content. Do you get what I'm saying? Yeah. So in this case, it doesn't make sense practically. The beta node. Okay. Any question on this? Okay. Now let's interpret the beta one. This is your linear models, what you've been doing. If this one there you have, once you run this one, so whether you finish or not, you have to answer. Yes.
So can we say if the head weight of the cabbage increases by at least 1 kilogram, the vitamin C content reduces by 7 points?
Good. That's exactly the interpretation. Remember, in the correlation, we realize that for heavier weight, the vitamin C content is what? Low. And so here, there is negative. So if we increase the weight by 1, we expect the vitamin C content to decrease by what? 7.576. So that's it. Exactly. Okay. So, yes. Any question on this? Is everybody okay? All right. Next, we need to check whether this model. Oh, I haven't finished. I'm in a hurry. Eh? More than. Okay. So now we've been able to interpret them. Now let's see. These are the standard errors. And we can also check whether we should include the intercept in the model. So I'm sure you will talk about tests concerning the parameters of the model. So is beta not equal to 0? We can test that with this t value. That's the t. Also, we can also test whether beta 1 is equal to 0. If beta 1 is equal to 0, then there is no relationship between what? The vitamin C content and head weight. In other words, if you take the content, it's just some random, a constant plus some random error. That's what it is. So in this case, yes.
So the beta, you can check that with the t value.
Yes. Yeah.
B1.
The same. So each of them has its t values. So we can also read from tables and also check whether that hypothesis should be accepted or not. But we have the p values here, so we can go with it. So if you look at the p values, the two of them, they are quite small. Is that okay? So we will reject the null hypothesis that they are all equal to 0, which means each of them is significant, and we must keep them in the model. Is everybody okay with this? Yeah, so, yes. Okay, so you've done this one, that if you have this model, you can check H naught, beta naught is equal to 0 against H1, beta naught is not equal to 0. That's the test we are doing. So we use the p-value. The p-value is very small. It says less than even that one. So you need 15 zeros 0.0015. So you reject the null hypothesis, which means beta naught is not equal to 0, so it must be maintained in the equation. And we do the same thing for the head weight. It's also very small, so we reject beta 1 is equal to 0. So that's it. When we get to the multiple regression, we may have beta 1 and another one, and then we can also check if you hold one constant, what is the other, and so forth. Okay, so that's it with these two. So we've talked about it. Okay, next is the residuals. So the residual standard square is this, and it has 58 degrees of freedom. Okay, so if we are conducting testing and so forth, we can use that. Now what is important here is multiple R squared and adjusted R squared. What is the difference? Oh, you have not done it yet? You have. Okay, good. Okay. Yeah. Then go outside. Okay, so how would we interpret this? We got the multiple R squared to be 0.4355. How are we going to interpret this?
So 43.5% of the variation in vitamin C
Yes.
is explained by the one.
Let's explain, yeah. So when we regress the vitamin C on the head weight is able to explain 43.5% of the variation within the values of what? The vitamin C. Which means the other almost 56% is unexplained. Which means if we want to explain, we have to add more variable. Okay. And that ties in with the adjusted R squared. As soon as we add any variable to it, the R squared will increase. But the adjusted R squared will take into consideration the variable you are adding, what is its relationship with the vitamin C content to increase it. So usually the increase in the adjusted R squared is moderate compared to the multiple R squared. Okay. Then the last one is that what we call the lack of fit test. The lack of fit test in the simple linear regression is the same as testing whether the beta 1 is 0. But when we get to multiple regression, there is a difference between them. So remember that we rejected the hypothesis that beta 1 is equal to 0. So it means that the regression is significant. So look at the results of the F test. So this is testing overall, and look at the p-value. The p-value is also small. So what do we reject the assumption that there is no the model is not good. And accept that or conclude that it is actually significant. So that's it with this. We can also do what we call the diagnostics to check the assumptions and so forth. So one of them is a histogram. We can actually do a histogram of the residuals. So if you put the model over there, it will give you the residuals. Sorry. I got something. Yeah, so it has to be residuals of this. So you want this to approach normal, right? and so forth. So if you look at this, well, it looks like a normal distribution, but not quite. Okay. But we can also do a plot of the model. If you just put the model in plot, it will just be giving you what? The diagnosis within it. So usually it prompts you to press enter and then it gives you the first. So you see residual versus fitted model. We expect this to be uniformly distributed. We don't expect to get trends in it. So if you look at this one, well, it's somehow evenly distributed, but not quite. Because if you look over here, there's nothing over there, over here, but the top ones, there are some of those things. And it tells you that the 54. So if you go to the model, or no, the data, and you check the number 54, you realize that it is quite distinct from the others. Similarly, 15 and I think 13. Yes, you will get those values. You will see that they are quite distinct from it. So those are the things the values that are given it. Then we have also KOKO plus. Remember we talked about KOKO plus, right? If the model is good, we expect it to give us the KOKO plot of the residuals to close to normal. That's what we use. We checked it from the histogram. It didn't look too normal, but not also, it did not also deviate so much from the, yes. Yes. It went, which one?
It's rather went like it's not like maximum, not minimum.
For which one? This one. Check the way, is it fitted values and the receipt?
No, it was comparing something else.
Something else, okay.
No, you press play
Yeah, so there are four graphs that must appear. So we have this one too, that's a scale. So standardized residuals and so forth. That one looks like this. But all of them, you can see vividly a significant trend within them. It's like they are distributed randomly within what? The space. And then lastly, we get the residual versus leverage. Okay, so you see that some of the values, like 51, 54, 44, they have what? Some larger distance. They are a bit distinct from the value. So these are all diagnoses that we can check concerning our model. What I want you to do is that when you go home, you can look at this. So we want the best, we can add the date and the cause, even though they are qualitative data, they can also explain the relationship between what? The model. So we can do that. Please do that and let's see. And then, yeah, you can try some other data. So when I meet you next week, we will do what we call bootstrap. We will use linear models to do so. So for example, if we can do those that have studied economics, maybe income distributions and so forth. If we want to fit a linear model, means will not be good. Sometimes you have to do quantile regressions and so forth. So look at that as well. So please, the assignment, I will put it on Sakai. It is important you submit. Yes, there's the first one and there's this one. The last week's own. Okay, I'll put it on Sakai. I'll put it on Sakai. Please make sure you do it. Yes, I said in groups, yes. So please do it and then.
The first group will be different from the second group.